Good morning, everyone. Lovely to see all of you here in the room today. We have another historical figure for our week, and this man is one of the fathers of algorithms. It is, of course, Don Knuth, and he is one of the key people who developed the field of algorithm analysis. He was born in 1938, and in common with one of the conversations I just had with someone coming into the room, he actually worked as a cryptographer at the National Security Agency during his life. One fun fact about him is he does not use email because he finds it too distracting, which is something you can do if you're quite famous enough to have your secretary print off all the most important things that come into your inbox and then you can reply to them. He did win a Turing Award, and he invented TeX, which is the precursor to LaTeX, the typesetting language that probably a lot of your math assignments are written in. Along with all of this, he also wrote these textbooks called The Art of Computer Programming, which a lot of algorithmic analysis and a lot of algorithms were actually developed in. So for some of the material in the class, I've actually gone back and looked at the original texts, which, while somewhat out of date with respect to modern techniques for algorithm analysis, still contain a lot of fundamentals and indeed some theorems that haven't yet been superseded, along with some open questions. Can anyone read what it says at the bottom there? So Don Knuth is actually known for being a big friend to China and has spent a lot of time over there working on developing Chinese computer science. And so he was given an honorary Chinese name by some of his collaborators. So Don Knuth is going to be our inspiration for some of the next couple of weeks of class as we start to delve into more complex algorithms, more interesting data structures, and take our work further. So we remember at the end of last week, I think it was Tim had a bit of a question. He said, well, we have our linked lists, and every linked list has how many pointers for each node? How many pointers for each node? So we could have one pointer forwards and one pointer back if we were using a doubly linked list. But Tim asked, well, what happens if we want a multi-dimensional data structure? What happens if instead we want to allow extra pointers to come out from our linked list and say it can go different directions? So moving on from Tim's question, let's use it to actually tackle a real problem. And so in this case, we have a beautiful ape on screen who wants to know which of his descendants lived to 13. And now this is a very computationally sophisticated ape, and so he's going to be using a computer to solve this problem. So let's say he's got all of his friends. We have a good collection of apes. Sun Wukong is 500, the oldest ape in the list. We have, that should be Mojo Jojo, he's only 4, and they are all his descendants. Naruto gave birth to Rafiki and Sun Wukong, and you can chart it all out. And in fact, this is probably not the best way of representing our data. How do we normally represent descendants and children? What kind of data structure do you normally use? Not even on a computer. And Danny's got an answer. A family tree. So that's going to be our inspiration here. We are going to develop a tree data structure which has the ability to map out, okay, you have a certain parent and that parent has children. And that's going to be the analogy that we use to actually create our data structure. Now, we've all seen family trees before, so we could probably extrapolate from that what the version of it represented in C looks like. So Danny, you've still got the microphone. So let's say we have a node to represent one person in our family tree. What should we have pointers for coming off that person?
Each of their children.
We should have children. Now, in the particular type of tree that we're going to start with, we're going to restrict it to just 2 children to make our lives a bit easier. So a parent can have 0 children, it can have 1 children, or it can have 2 children. And because we like to play favorites in this class, we're going to have a left child and a right child. And you can decide for yourselves which child you think is better. I'm left-handed, so I'm going to always side with the left children. So let's go back a minute to our original problem, which was how do we find the oldest descendant in the set of descendants? So we could recap a little bit and go back to the way that we used to do this. So previously, how would we find an element or the largest element in a sorted list. And let's take this back pretty far today. Okay, so Rochelle, what do we do if we have a sorted list of things? How do we find the largest item, which in this case is going to be the oldest monkey? I guess my remote doesn't work from here. You have a sorted list. What steps do you do to find the largest one?
Calculate the character.
Say a bit louder.
Character.
So what do we do with the characters?
Calculate the number of the characters.
So they're in order from, let's say, smallest to largest. So how do you find the largest one?
Have the largest number.
Which we can do just by looking at the end of the list, right? Because they're going, if the numbers are getting bigger each time, we just go to the end and that should be the biggest number out of all of them. So if we know how long the list is, how many steps does it take us to go to the end? If we're using an array, let's say.
N.
Well, it shouldn't take us n, because if we know that you can write in C or in any programming language, if you want to get the 7th item in the list, and you know there are only 7 items in the list, it only takes you 1 step. You just ask the computer for item number 7. Now let's ask, it was Kavir? Yeah. Okay, so let's say instead of using an array, we're now using a linked list. And let's say it's still sorted. How long does it take us to get to that last item?
Will it be the same? So only 1 step to reach it if we know it's the last item, right?
So can you jump anywhere you like in a linked list? No. So let's say we're starting at the head of the linked list. How many steps does it take us to get to the tail if there are n items in the list?
N.
It takes us n. Now, we did have an exception to this. We talked about doubly linked lists. How many steps would it take us if we were using a doubly linked list and we kept a pointer for both the head and the tail?
N squared.
Well, it shouldn't take us n squared really, because we know where the last element is, that's the tail. We know where the first element is, that's the head. And we know that the last element is the one we want. So how many steps should it take?
I'm not sure, honestly.
It should just take us 1 step, because we know where the last element is, and we know that's the one we want. So we can just jump right to it. It's just like with our array. And it was Rochelle. I've got it now locked in my brain. So for our different data structures, we're going to have different properties to try and find the last element, so long, and this is the big catch, so long as our list is already sorted. Now that's a very big catch, because we know that sorting, for at least all the algorithms we've seen thus far, runs in worst case O of n squared. So we're going to have to do n squared work, and then after that, we're then going to have to do our O of 1 for an array. So we haven't really saved very much. We're kind of doing it in n squared. Now, what if we are trying to find an arbitrary item in a sorted array? How long does that take us? Gabriel, we haven't heard from you in a bit. So let's say I want you to find if the number 13 is in a sorted array. How long is that going to take me?
Worst case scenario, it's going to take as many elements in the array.
Well, it's sorted, so I've given you some extra information. What algorithm do we have that works? Maybe Harwin, what algorithm do you know that works on a sorted list that allows us to find something fast? Binary search, that's great. And how long does binary search take? Log n time. So that's going to be our solution for, oh, there we go, for if we already have it sorted and we're looking for an arbitrary element. But then again, having it sorted means that we've already done, at least thus far, n squared work. So we're still not really winning. That's n squared plus log n, and that's big O of n squared still. Now we are going to find a faster sorting algorithm soon, but we have to be really careful here that we're actually saving ourselves work overall. You can't say, assume it's sorted in every case. So this is where we're going to introduce binary search trees. And this is going to give us a way to actually solve this problem and actually develop a tool that's going to allow us to do searches quite efficiently. So beyond the prior rule that we just had, that a parent can have at most 2 children, we're going to introduce one additional rule. And that's the following: that all the children and all the descendants on the right should be older than the ones on than the parent, and then everything on the left should be younger than the parent. Now that might seem a little funny because parents and children, normally there's some age associated with that, but let's follow this rule for the purpose of our task. So I'm about to present to you the ape tree. So we have all our apes, and our goal here is still to find the oldest descendant. And the way this is going to work is, again, following this binary search tree property. And why binary search tree? Well, it's a tree. It's got parents and children. It's binary because you can have at most 2 children, so child 0 and child 1, so there are 2 of them. That's what binary means. And then it's a search tree because of this property that we've added to it, where everything on the right of the parent must be larger, everything to the left of the parent must be smaller. So if we look up here at Rafiki, everything on Rafiki's, I guess it's the other way around here. So everything on this side of Rafiki is smaller, and everything on that side of Rafiki is larger. So 40 and 34 are larger than 33, and 27, 22, and 21 are larger than 33. And we can look somewhere else as well to check that this property holds. So let's look at Mojo Jojo. Mojo Jojo to his left is everything smaller. So now what is the runtime to find the oldest ape? How many steps is it going to take us to find the largest value in this tree?
Would it just be 2 steps?
So in this case, it is 2 steps. Chart it out for me.
You go from 20 to 33, and then 33 to 40.
And how did you arrive at that logic?
Because you know that only the right subtree would be... you can only go right to increase. I mean, an increase will only be on the right of the parent.
So let's say we start at what we'll call the root. And trees have roots. The root is going to be at the top here, which is a little funny, but that's the way computer scientists do trees. We do them upside down. So we start at the root over here, and if the root has no children, have we found the largest element?
Yeah.
Yeah, because there's only one element there, it must be the largest. If the root has no right children, have we found the largest element? Yeah. Why?
Of the assumption that the left subtree will always be less than the value of the...
So we've got our property here that says, if there is anything larger than the parent, it must be to the right.
Yeah.
So if there is anything larger than 20, it must be to the right. And if there is something to the right, it also must be larger than the parent. So both of those things are true, which means we have to go down to the right. Now we get to another node, and we can imagine that this is just the root of its own tree. It is the root of all the children, all its descendants that come after it. So we can do the same logic again. We know by the fact that it has a right child that child must be larger than itself. So 40 is larger than 33. Great, let's follow that. And now we're at our last subtree. So we have the root of our subtree. Does it have a right child? No right child, which means the element that we're looking at must be the largest element because anything to the left, we know by definition of our binary search tree property, must be smaller. So 34 is smaller than 40, and this is one of the properties that we've aimed to preserve in the construction of our tree. And so if every node that we've followed has been larger than all the prior ones, and there are no greater ones that we can get to, we have found the largest element in the entire tree.
Isn't it 3 steps instead of 2 steps? Because at the last 40, you still have to check if there are any to the right.
So it depends exactly how you're counting it. Do you count checking if the root has children, or do you only count from that point? But the point is really the big O behavior. So you could argue that, well, you check the root and you have to check its children, so it's how many, you might be counting how many children checks are you doing, so then that would be 1, 2, 3.
Yeah. Okay.
But if you're starting from the presumption that the root is not the largest one, then you're kind of doing 2.
Yeah.
So you've still got the microphone, so we'll carry on with you. What is the big O runtime of this?
Probably log n, because it's it's cut it down into like choices of 2 each time.
So you've jumped ahead a little bit, and it looks like it might be log n, because I think Gav's argument is, well, each parent has 2 children, and so each time you go down, you're splitting the number of possible items at that level in 2, and so the furthest you can go down is log 2n, because how many times can you split the whole thing into 2? You can only do that log 2n times. But there's an assumption there. Do all parents have 2 children?
No.
Okay, so what's our worst case here, really? If every parent has, what is worst? If a parent has 2 children, we end up saving work at each level. If a parent has 0 children, well, that's even better.
Yeah.
What's the worst case?
So worst case is still log n, isn't it?
Well, worst case is if every parent has how many children?
2 children.
No, that's not the worst case. That's a good case for us, because then in each case we're eliminating half of it.
Oh, right. So worst case is if every parent only has 1 child.
Yeah, and if every parent only has 1 child, let's see, I'm going to jump to this. If every parent only has 1 child, what is the runtime of finding the oldest ape?
Still O of n.
It's O of n. So the speed up that we get is going to be based on how many children each parent has. And so that means in our absolute best world, every parent is always going to have 2 children, or at least as much as possible given the number of nodes we have. So it might be the case that some parents at the very end of the tree end up stragglers and have no children, but ideally, or only 1 child because they're the one at the very end. But in our perfect world, we get what we called a balanced tree, where we fill it out as much as possible, and then we're going to get the log n behavior. Yeah. So our binary trees are actually going to behave really interestingly here, because the worst case runtime is going to depend on what we call the height of the tree, which is the maximum number of hops that you need to go to get from the top to the bottom. So in this case, we can see that we have a height of 5, because we have 1 node at the top, and then if you take this path, 1, 2, 3, 4, 5, that is the furthest down that you can possibly go, the furthest number of steps that you can get away from the top of the tree. So assuming that our items are distributed in a random fashion, we will get log n, O of log n average case behavior, because we're expecting more or less for half the elements to be bigger or smaller than any other than a given parent. But again, we're worried about the pathology that we could get with the stick behavior. So let's jump back a little bit. So we can repeat the same kind of process we've been doing, not just to find the oldest or youngest ape, but also to find an ape with a specific age. So let's look here, and Garb, do you want to pass it to Ed? Right next to you. Ed, what steps do we take to find the ape who is 22? So is 22 greater or smaller than 20?
22 is greater.
Okay, greater, so which direction do we go?
You'd go to the right.
Go to the right, so let's select the 33. Is 22 greater or smaller than 33?
Smaller.
So
go to the left.
Go to the left.
Smaller than 27, so go to the left again, and you've got it.
And we've got it. So it took us 1, 2, 3, 4 steps. So we checked the node we're at. Is it 22? No. We go to the right. Is it greater or is this 22 or is it greater or smaller? It's not. Follow the left, and then we eventually find it. So our worst case behavior, both for both the behavior of find the largest item and for find an arbitrary item, we're both going to be O of n, which is in the case where your tree is actually a stick. And you can see why it's a stick, it kind of looks like one. So unfortunately, in this class, we're not going to teach you how to create a balanced binary search tree or how to ensure that as you add and remove items, you get a balanced tree. That is going to be the study of your more advanced algorithms classes. And you can actually do even better in terms of figuring out the optimal binary tree design for a given pattern of data. And that turns out to be an area of active research. So I'm going to now, with what we've learned so far, you're going to have a couple minutes and we are actually going to give you a chance to design your own algorithm. We'll take a little bit of time to do this. So here we have the data structure in C that we could, or one version of the data structure that we could use to represent a node in our tree. And just like with the linked list, where the full linked list just stemmed out of our definition from a single node, so too with the tree. So you'll notice instead of having a single pointer to the next element, we now have a pointer for the left child and a pointer for the right child. So I'm going to give you all 5 minutes with in pairs, or if you're not in a pair, you can work on your own. Or if you're in a group of 3, you can cluster in 3. But I want you to come up with at least one of these 2 algorithms for finding a given item in a binary search tree. Okay, well, I've heard a few good ideas out there in the audience. We're going to go with Arthur to talk us through his idea for the recursive version. And we're actually going to try and see if we can code it live, which will be a bit of an adventure for all of us. What I will say is I'm not going to attempt to run this code because I think we're not going to get all the way there that fast. Oh. Okay, so let's start off. We'll get to you in a second. Let's start off with our code from before. Typedef struct node t, and then struct node. And let's make our lives easier for the time being, and let's just store an integer. Okay, so what's the very first thing I need with a function, Arthur? Oh, so yeah, if we want to print stuff out, let's just assume I've done that, and let's write our function. So what do I need for any function? Okay, so what would be a reasonable name and type for this? Call it what tree? Arthur tree? Okay. I think a more sensible name, I like that name, no objection to it, but maybe let's call it find recursive. Might make a little more sense. And what arguments do we need to it? So int target. So we need a node. And should that be a pointer or not a pointer? Probably a pointer. We don't want to be copying the whole tree every time and have them all the nodes embedded in each other. That's not going to work. So let's do it this way. Okay, now you said you had the recursive thing, the recursive version. What does every recursive function need? Well, it needs to call itself, but the other thing it needs? I heard it, was it Sam that said it out loud? I don't know who said it, it was Tim. It needs a base case, right? It needs a case when it's not going to call itself, otherwise we'll get infinite recursion. So in this case, what's our base case? When do we stop? Okay, so how do I write that in C?
If your current position is larger than your target.
So wait a second, slow down, I'm writing this in C, if current, just like that. Is that right? Well, let's look at what current is. Current is a node T. But that'll give me a struct. And I'm not checking if the struct is larger or smaller. What do I want to check? I want to check the thing in the struct, which is called data. So let's use our trick for dereferencing and getting an element at the same time. So if car data equals target, then what do I want to do? And then what am I going to return? So in this case, let's make our lives a little bit easier. And I am going to return 0 for it has been found, but I will maybe print here, we found it. So we're not actually going to do anything. We're not going to save the index. I can show you later on how to make more use of this, but for the time being, we're just checking if it's actually in there or not. That's going to be what our function does. Okay, so let's say we didn't, it wasn't the current element. We have a decision to make. And what's the decision?
The decision is that your current position is larger or smaller than your target.
So that's the check. What's the actual decision that we're making as a result of the check?
You move to the left or to the right.
Yeah, so we want to determine if to move left or right, and you just said it. How do we figure out if to move left or right?
If your current position is larger than your target, you move to the left one.
Okay, if current is larger than target, that means the target is smaller than the current one, and all the smaller things are to the left. Okay, so how do we run this recursively on the left half?
So your current position goes to left, right? It's
Okay, so we could do something like this. Car equals car left, but then what?
and then you should still call the find recursive.
Yeah, so I actually need to make the recursive call. So instead of doing actually changing car, because we're not going to use it again in this function, let's just make our recursive call right here. Target car left. And then the other thing we want to do is we probably want to return it. We want the outcome of that. Now, what is a problem here? What assumption am I making?
There is something that is not
Yeah.
active.
So what do I want to do if there's not actually something to the left?
You're gonna return if there's nothing to the left, which means you haven't found the target.
Yeah, so if there's nothing to the left, but I needed to go to the left, that means the item's not there in the tree at all. So we can check if not car left, return 1, and then printf not found. Now, obviously, if you were writing this for real, you wouldn't just want to return 0 and 1, you'd want to hash define these values, but because we're kind of coding it on the fly, we can do it this way. And then if, what's our other branch? Let's do this one quickly.
Our current is smaller than target. Then it goes to right.
What do we want to do before we go to the right? What do we have to check? So we can replicate this code. If nothing on the right, not found. Otherwise, go to the right. Now, does anyone see bugs in my code? I haven't, but there might be a bug. Garv. Oh, find rec. Okay. That is a more minor bug. Any other bugs? So it doesn't need to be if else, but it does make sense. It'll still run correctly, the logic works, but it would make sense to do it that way. So that is nice because you're then combining the two logical conditions together, but we can clean up this code a whole lot. Our point is to get the algorithm. Tim, is there another bug? Yeah, so this can be refactored a lot more nicely. The goal here is not to show you the cleanest version of the code, it's to guide you through a process that you might go through developing an algorithm like this for the first time. And then what we do after is we can take another look at it, and maybe let's actually get Tim's suggestion.
Notice that we have repeated some code. Yeah. Which is that we have a check if car, or rather if not car left, not found, return 1. And we also do it again, if not car right, not found, return 1.
Yep.
But if this instance is recursive, we could just put this into its own condition at the start of the function, and so let it call find rec on left, and then it will tell us when it calls that, actually this doesn't exist, so therefore we can just just have that once.
So let's actually follow Tim's suggestion. Let's delete that. So Tim said, well, you actually can make this function call. And so when we start find rec, we can check, what do we need to check?
That car data exists, so if not...
Is it car data that needs to exist? So look at the stuff we just deleted. We just deleted these statements.
Car exists because we want to know whether it's not null, essentially.
Yeah, so we have to check if the item that was passed in is actually a valid item at all. So if, or the node, I should say, if not car, printf not found, return 1. And that is a much cleaner way of writing it, but required us to develop it a little more slowly and then make the optimization after. The iterative version of our code is actually just as easy to work through, but the logic looks slightly different. I'll show it up on screen. We were only going to look at one of them as the way we developed it ourselves. Okay. So this is a simple representation of the iterative version. So here we just have a while loop, and each time, in this case, instead of using a variable called car, I've called it p. So set p to be the root, and then each time just update p whether to go right or left. So that's a representation of the iterative version. And this is a representative of the recursive version. Again, this version is just nice and short, so it fits on the slide. So what about for insertion? Insertion and deletion for binary search trees get a little bit more complicated because now we're actually potentially putting in something or removing something from our data structure that isn't in the right place when we first put it in. So with an array, if you lop something on the end of the array, there's no rule to say, well, you have to have only bigger items at the end of the array or only smaller items at the end of the array, unless it's already sorted, in which case we've already talked about how to reshuffle things. For a binary search tree, you're actually going to have to do work every time you put something in and every time you take something out. Why would we do this, you might ask? Like, why would we do this, you might ask? Because we didn't have to do this with arrays or with unstructured collections of data. Why are we paying this extra cost? And the answer is paying the extra cost upfront for each of these operations for add and delete is going to make things like searching really fast. Because we saw that searching was going to be, on an average case, log n. So by doing this extra work for insertions and deletions, that allows us to actually get that log n behavior on the operation that we think is going to be more common. So if you are going to be doing adds all the time, maybe this isn't the right data structure for you. However, if you're going to be using searches all the time, then you're willing to pay a bit of a cost to make adding and deleting a bit more complicated in return for getting that better time on the searches, which typically in the real world is something that we do more frequently than adds and deletions in a lot of different use cases. So our insertion code also has multiple cases, and that's because when we look at the different places in which an item could be inserted, they're going to result in different conditions. So this is my very sketchy code, just like the sketchy code was up before, for how the first part of insertion is going to work. So this code is only going to work if the root exists. I'm skipping out some checks here just to make it nice and simple. So the first thing we want to look at, this is pseudocode, is the item that we want to insert bigger or smaller than the current item we're looking at? If it is bigger, then what we can do is we can do this recursively and insert it on the left subtree. If it is smaller, then we insert it on the right subtree. So this is the same kind of thing as we were doing right before when we were deciding which direction to go, only this time we're doing it with insertion. But let's look at our ape tree again and try and figure out how this would work. So let's say we want to insert 28. Is 28, who's got the microphones? We've got one with Tim. Tim, do you want to pass it next to you? And your name is one I always forget, so you'll have to remind me. Sissa, that's right. Sissa, is 28 greater or smaller than 20? Greater is, okay, so that takes us over here. Is it greater or smaller than 33? It's on the left. Now, is it greater or smaller than 27? So where does it go? Well, is there a tree on the right for us to go down? So what do? Where does 28 belong? You answered me correctly a second ago. I asked you the same question. It belongs on the right, yeah. So because there's nothing there and it belongs there, what should we just do?
Just create one.
Yeah, and the way we create it, we have our C structure, which was, let's take a look. For any given node, we have a pointer. We have a pointer that allows us to put something on the left, and a pointer that allows us to put something on the right. So in our instance, what are we going to do with node 27?
We can just put value to the pointer of the right.
Yes, so we have node 28, and so 27's right pointer, we're going to set the right pointer of 27 to point to node 28. And that's what we do right here. And you can do this throughout the entire tree. So we can do, if it goes down and was smaller than 27, so let's say we're trying to put 20 on there, what would we have done? So if we're trying to insert 20 now instead of 28. So 20 would actually take us all the way back up to the top here.
Oh, true, yeah.
Right? So we have to make sure that we're not just following with our logic from where we were down below. So 20 is a duplicate value. So if we look at our way back here, what did we say for duplicates? We said that for this version of it, we're going to put duplicates to make sure that that's always on the right. So this is going to be a slightly trickier case. So let's go back to here. So where would we put 20? It should be on the right, but what happens when we get to 33? It's smaller than 33, so it should be to the left of 33. It should be to the left or right of 27? Left of 27 should be left of 22? Left of 21? And so where does it end up? Yep, just in that spot down the bottom there. So it is Donkey Kong's left child. And so kind of interestingly, our duplicate item has ended up relatively far away from its original parent. But as long as our binary search tree property holds, this tree is still going to be valid. Okay, now let's do deletion, which is even more complicated. So this is our pseudocode for deletion, which again is not going to work to delete the root. You're going to have to handle the memory a little more, in a bit more of a sophisticated way for that. So the first thing we need to do for deletion is we're going to need to keep track of the parent. So this was just like in linked list insertion and deletion, where sometimes you needed to keep track of the item before the one you're inserting so that you can fix up the links after the fact. So if you're deleting something and you take it out, you need to know where to attach the remaining stuff to. So in this case, the first thing we do is find the parent. And then what we do is we figure out whether the item that we're about to delete is the left child of something or is it the right child of something. You want to know the link that's coming out of your parent, Was it a left link that led to U, or was it a right link that led to U? So let's look at an example. In this case, we're trying to delete 21, which makes its parent 22. And so it was 21 on the left or the right of 22? It's on the left of 22. And so it's the smaller child, and so we set this variable on left equal to true. So if it is on the left, then we go to the parent and we just say, well, now there should be nothing left on the left of the parent. Otherwise, it should be that there should be nothing now on the right. So we've just deleted that node there. Now, this only works assuming that the element we just deleted had no children. Because if our element did have children, we've just made that entire subtree disappear. So we've deleted what was on our parent's left without actually reattaching the children correctly. So now we need to handle that case. So let's now try and delete element 22. So in this case, we are the left child of 27, but we have our own left child. And so what makes sense to do, where's my microphones? Gabriel, do you still have a microphone? Let's pass it to Ray Ray. Okay, Ray Ray, if I want to delete 22, what do I need to fix?
You want the left pointer from 27 to point to 22's child, 21?
Yeah, perfectly right. So if we're going to disappear 22, we need to make sure that we don't abandon 21. So what we're going to do is, because we just have one child, that's a very easy thing for us to fix. We just attach that child to the parent. So if 22 only has a left child and we were on the left, attach 22's left child to its parent. Okay, now we have the version where if it has a right child. So let's look at this one where 33 has a right child and we're trying to delete it. Is the next item in the binary search tree as compared to 33. So I've put 34 in there and I've swapped them around. But now I still want to delete 33. That's still the element I want to delete. So I've swapped it up. There we go. And now I can delete 33 because it only has one child. So we're in an easy case. If we only have one child and we're on the left or on the right, we can just figure out how to attach that correctly. If it's not the case and we have both children to deal with, what we're actually going to do is we're going to find the right node to put in that, the correct node to put in that place. I should be careful with my left and rights here. And the way we do this is by finding the successor to the node that we're trying to delete. So that's the next node in the ordering. So for example, if you have a list that contains 7, 10, 12, and 34, the successor of 10 is 12 because it's like the next biggest item. And so what we're going to do is we swap X with the successor, and that allows us to make sure that we're actually going to keep the binary search tree property. Otherwise, if we're just swapping random nodes into there based on our choice between them, we might end up swapping a node in there that means that the binary search tree property is broken, because otherwise we don't get that guarantee. So just like we had our list ops pre-written functions for you, in this class we also do have the same thing for tree ops. The expectation is not that you would be able to write all of these from scratch very easily. It is still fair game to ask you on the exam to reason through one of them, but we have provided you with pre-made code for tree ops. So let's take a brief look at it. And in this case, we're using a binary search tree to count words and print a sorted list of words and their frequencies. So we've seen our word count example a few times in a few different ways, and this time we're doing it with a binary search tree. So let's look at tree ops. This is going to be very similar to our list ops. So we have similar looking code to make the empty tree. We create the node, we malloc some memory for it, we set the tree to be empty initially, And in this case, one interesting thing that we're actually going to do is we're going to use a function pointer to allow us to store within the tree itself how to do comparisons between the different items. So this allows us to do the polymorphism trick that we were talking about before. And if you have data void star data t, you want to allow data t to be an integer, you want to allow it to be a string, but we still only want to have written our tree code once. We don't want to rewrite our tree code for if the item is a string, if the item is an integer type. And the way we get around that, given that we're going to, when using the tree, we're going to be comparing items all the time, we're actually going to save the information about how to compare the given type of items within the tree itself. So if we look at treeops.h, our tree structure has a pointer to the root, but it also has a function pointer. And this function pointer is going to say, okay, this type of tree that we're making is a string tree. This type of tree that we're making is an integer tree. And when you create it, you're going to give the makeEmptyTree function a pointer to a function that would allow your tree to compare the given data type you're using. So if it's an integer tree, we've got to give it a function that would compare integers. If it's a string tree, we've got to give it a function that would allow it to compare strings. And so in this way, we're actually using functions as kind of an object that we can pass around in our code, which is quite exciting. Then we have a function just to check if the tree is empty. So given a tree struct, check if the root pointer is present or is non-void. We have our recursive search tree function, which looks very similar to what we just wrote, only now we're using that function pointer contained within the tree itself. So our recursive search tree will take the root, the target that we're looking for, the function pointer, and then instead of just writing something like is key bigger than root, we're using our comparison function. And remember, our comparison function is going to return 0 if the items are the same, or 1 or a positive value or negative value depending on which item is larger. So this looks very, very similar to the code that Arthur helped us create from scratch, only now we've substituted in the function pointer. Likewise, search tree is going to be just a little helper function that feeds in automatically for us the root, the target, and the comparison function. So you can look over the different functions and compare them against what we showed in class. So now we have a relatively efficient way to do binary searches over and over and over again, and we have built up a structure that kind of mirrors the algorithmic process that we were doing before. And this actually reflects something really deep and interesting in algorithms, is that you can have an algorithm that operates without a given data, without like a specialized data structure. So we had our binary search that works just on our arrays, but there seems to be this very deep connection between the rules of the structure we just created and the particular algorithm that it's useful for. And we'll find this over and over, that just like we had versions of the find repeats algorithm that worked without the data structure, in essence, some of what they were doing could be replicated through a representation of data that reflected that particular process. But it's not always obvious what the rules to make that data structure are in comparison to the particular algorithm that you're using. And so there are a lot of interesting research papers that reflect on this kind of comparison. Okay, let's stop for a second and take any questions.
Yeah, so imagine the tree's like, 10 layers deep, like a really big tree. Yeah. Still balanced and all, but very deep. I was wondering, like, you can start on the top and go left, right, left, right, left, 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 right, 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 right. Or is it possible to say, actually, we're going to make an educated guess and we're going to go somewhere deep in the tree, like halfway depth down the tree, and then start from there. And, okay, if it's greater than or less than, we're going to make a much bigger jump than just like going down like one tree at a time. Is that possible, or is that down the wrong path?
So if you at least look at the representation that we're using in C right now, we only have, when we start off our algorithms, we have access to one pointer to one node, and that's the root. So we don't actually know how to jump in the tree, at least using this representation. So let's shift our motivating question a little bit. So to how old did Mojo Jojo live? And so we're going to again assume that we have some structs that have the name of the ape and the age to which they lived. The question for now is what data structure is going to be best used to answer this question, which is a little different. Saying you know the name of the ape that you want to find some information about. What is the best way of getting information about that particular struct that corresponds to a given name? Does anyone know of, perhaps in a prior class, I know many of you have taken Comp 101, what data structure would you use to do something like this? Dictionary. So anyone else? Hash table or dictionary, says Ronald. That's the correct answer, but that only kind of like, if all you know is Python, that's only half the answer. I think a better way to think about these kinds of questions is what functions should it have? Now, where have we got a microphone still? So let's say we have a set of names and we have a set of ages corresponding to those names, and for a given person, we want to figure out what age they are. What functions should our data structure support? So remember, like for our queue, we had remove from front, add to back. So for this data structure, what functions should we add?
We are trying to get the age of a person inside a dictionary, right?
Yeah.
Like that, right? Something works with index?
So kind of, but the thing is we don't know at what index in like an array or anything that any of our objects are at. What we do instead know is the names. So what do we want our function to do? Okay, what's the input of the function?
So the name of the...
The name, and what's the output? The age. So we have a kind of a matching. We've got what we'll call a key, which is the thing that we know already ahead of time, and we have the value, which is the thing we're trying to get. And so that probably makes sense for the name of our operation could be get, and the get function should take in a key and it should output a value. Now, because this is a dynamic data structure, we're not content with just the ones we have. What other functions should our data structure support? Just like the queue supported adding and removing, we probably also need, Andre?
A get function?
So we've got our get function, which given we give it a key, it gives us back a value. What other things do we need to be able to do with our data structure? I just said it.
Wait.
So we want to be able to add and remove items. And so our next couple minutes break is, let's say I have told you that you can use all of these different things to build a dictionary. So we're going to have our insertion, our deletion, and our search operation, which is this get operation. What I want you to do is fill out the table with the big O runtimes for each of these. So you have a couple minutes now to do that. And we will stop that at roughly 10 past 12. Okay, Chris, can you help us fill out a few of these? So you can pick which row you want to do.
Okay, I'll do the unsorted array.
Okay, unsorted array. How long does it take to insert an item in an unsorted array?
If it's unsorted, then probably just like 01.
01, you just insert it at the end, you don't have to do any work, that's all fine. Okay, what about to find a given item? So let's say we want to find Mojo Jojo in there and pick out the age from his struct.
Okay, so is this search, unsorted array for search?
Yep, unsorted array search.
It's ofn.
Oven, because we don't know where it is. It could be at the end, it could be at the beginning. We have to at least go through and check every item. And for deletion?
Same ofn, because we also have to search which one to delete.
So O of n, if we don't know which one we want to delete, we've first got to go through, and even if we know the index at which we want to delete an item, why do we have to still take O of n?
It's because it could be like anywhere.
So let's say we're trying to delete the first item, we then have to move all the items up one slot. So it's going to take us a while. Do you have another row ready to discuss?
I mean, I have like sorted array as well.
Okay, pick another entry or two and we can discuss that.
Okay, let's go through a sorted array.
Go through the sorted array? Okay, sorted array. How long does it take to insert something into a sorted array?
So if it's sorted, it's O of n.
O of n, because we've got to figure out where in the array it should go. And let's say it is the biggest item and we're going from smallest to biggest, then we just put it at the end. That's our best case. But our worst case, if it's the smallest item and we need to put it at the beginning, then we have to first copy everything over one spot to make room to put it at the beginning. Okay, what about search in a sorted array?
If it's a search, then it's going to be log of n.
Log n, we do our binary search, and then deletion.
Yeah.
Deletion is?
Deletion is O of n.
O of n again, same kind of thing as we've just done. Okay, Maka, do you have the linked list or the binary search trees done?
The binary search tree, the worst case.
So binary search tree, worst case insertion.
O of n.
Yep, O of n.
Because each node only has one parent.
So this is our stick. This is essentially where it's just kind of acting like a very long array. What about search? In a stick.
O of n as well.
O of n as well. And deletion?
O of n as well.
Yeah, so our stick is pretty awful. Now, what about in our best case? Have you done that one?
I have an idea.
Okay, so our best case, how long did we say search took? We discussed a little bit.
Log n.
Yep, did I say average case? Yes, not best case. It takes log n, so it's just like doing a binary search, so that's our search one. And then what is our average case insertion?
Log n as well.
Log n as well, and our average case deletion?
Log n as well.
Log n, all the same reason, because the number of times we're expecting to have to go down to figure out where to put it is going to be log n steps. Deletions, the analysis is a little bit trickier because we have that find successor function, but you can trust me on that one for the minute. And then who's got the linked list one solved? Yep. O of 1 for linked list insertion, because the linked list isn't sorted, we're just putting it, we're just attaching it to the head. Then search in a linked list. O of n, because we have to follow the links along till we find the right one, and deletion. Depending on where the item is though, if I tell you to delete Mojo Jojo, and Mojo Jojo is somewhere in the middle of it, then it could take you O of n because you first have to get there. So it's only a small number, fixed number of steps, a constant number of steps once you get to the item, but assuming it's not the head or the tail, then you end up with a search to actually find it. Okay, so this was our...
Why is it that it's O of 1 in an unsorted array, but O of n in a sorted array? Would not we have to copy and push back if we wanted to preserve the old elements? Like, even though we're not, like, keeping it in sorted order, we still need to, like, not accidentally delete an element. Like,
so you can just put it at the end. If you know how long the array is, and you know there's space at the end, you just dump it on the end.
So you're saying because it's unsorted, insert should be interpreted as just like chuck it anywhere, it doesn't actually matter. Okay.
It's where can you...
Insert would be like, oh, I have a specific location that I want to shove it in.
Yeah, so in this case, we're just defining insertion as adding the item to the data structure. Which becomes important because for all the data structures that have some additional constraints imposed on them, like the sorted array in the binary search tree, then adding an item to the data structure means that you have to preserve the constraints that apply to that given data structure, which is both how you get the algorithmic benefits, but also what makes insertion and deletion more complicated. Okay, so I know the eras tour is over, it was Ella, and she's not with us today, but she was our Swiftie. But what I can say is that the year that the Eras Tour happened, I actually did give away Taylor Swift concert tickets to people involved in the class. But like any good professor, I've got to do this in a fair way. And, you know, first come, first serve doesn't do it for me here at the University of Melbourne. So we've got to figure out a way to do it based on grades. So I hope you're all working hard at assignment 2. Because I don't know who's going to be performing in Australia later this year, but tickets to that might depend on how assignment 2 goes. But I know you'll all do great. What we want to do, though, is assuming that, I don't know what that placeholder is in the corner there, placeholder for whichever artist is coming here this year. So let's assume that this is our goal. We want a data structure that's going to make it easy for me. There are 436 of you enrolled in the class. And I want some data structure that, let's say I have K tickets. I want to give it to the K people in the class who have the highest grade, and I want to do that efficiently without going through every single person in the class. So I want to throw all the people in the class into a data structure, and then 10 times in a row, I'm going to want to get successively who has the highest grades. And so just like our queue, if I have the people lined up in the correct order, I want the first person that I give a ticket to have the highest grade, then they can be removed. Then the next person have the highest grade, next highest grade, and so on and so forth until I've given K tickets away, depending on how much the University of Melbourne increases my pay in the next year. So we need a data structure for this. Would a queue work, and why or why not? And Tim, do you want to pass the microphone forward to Sam?
A queue might work, but only if it's a sorted queue with, like, from highest to lowest grades.
So what would happen if I was trying to use an unsorted queue?
The person at the front of the queue would have a random grade and they would get the first ticket, and that they have a high likelihood of not having the highest grade.
Yeah, so like I could do something weird, like ask the person what their grade is, store that in memory, get them to sit down, keep doing that until I've gone through everyone to figure out who the highest grade is, and then put them all back in the queue again. But that kind of defeats the purpose. That isn't the data structure doing the work, that's me doing the work. So we need something like a sorted queue, and what we call this in computer science terms is a priority queue. So whether it's grades, whether it is the order of importance, whatever it happens to be, it's some sorted version of the queue. Now, what operations should a sorted queue support or a priority queue support?
Probably like popping from the front of the queue.
So we need a way for me to give the ticket to the first person and then remove them?
Adding to the back of the queue specifically.
Yep. Well, do we add to the back in the case of a sorted queue?
Oh, no. You just add wherever it needs to go.
Yes. So just like our other data structures that we just talked about when filling out our table, we want to have a way to add a new element or insert a new element into our data structure while preserving the structure. So we need some version of our insert. And then another useful operation that we might have is just an isEmpty to determine if the data structure is null or not. So just like some of our other fancy data structures, like our tree, priority queues are an abstract data structure. That means you can implement them in multiple ways. Just like we showed that you could implement a tree using either pointers or with an array, you could implement, you can also implement version or using the array version. So, Sam, given that you volunteered yourself, how do you think you could create a priority queue?
You could do something similar to the binary search tree. Like, you have the first kind of element, and then the next thing that needs to be added, you check whether it's above or below, and you either connect it to the front or you connect it to the back. Like via pointers, you either have a pointer pointing back to the one you initially had, or you had a pointer from the one you initially had pointing back to the one you just added.
See, Sam, you're disappointing me here because this year's class is too good. I ask a question, I want the naive version, and I always get a more sophisticated version. So let's go to the less sophisticated answer that I was expecting. And this is the stupidest version that I can come up with, which is get the queue, sort the queue, and then every time that someone new comes, sort the queue again. And then when I'm ready to give a ticket, give a ticket from the front of the queue. And then every time that I remove someone, when I remove from the front, I'm not unsorting it. The rest of the people will still be sorted. But let's say that someone new comes, let's sort it again. And how much does sorting a group of elements cost me, Sam?
Was it n squared?
N squared, worst case so far, n log n, average case. So this is probably not good because every time we want to add someone, how much work do we do?
N squared or n log n, depending.
Yeah, so we're doing our sorting worst case time. We're doing our sorting time here, which is probably pretty bad because all we really need to do is figure out the right place for that person in the queue and then to shift everyone along accordingly. Now you can imagine a whole bunch of ways of doing this. The naive and more naive way might be just figuring out where in the queue they're meant to go and then pushing everyone back one. So this is naive version number 2. So sort everyone in the queue, whatever your starting elements are. If someone new comes back, fix the slightly unsorted queue now that they're here, so figure out how to do that. And then give tickets from the front of the queue and then fix the slightly unsorted queue, although it shouldn't really be unsorted at that point. So let's say we're implementing this version using an array. How long is this going to take? Each of our operations. So how long does it take to remove something from the front of an array?
Oven.
Oven. And let's say let's use the front of the array as the front of our queue for the time being. And then how long would it take us to insert something and figure out and push everything back?
Also oven.
Break it down for me. So how long does it take us to find the correct location to put a new item in a sorted array?
Oven to find the location.
Find a location in a sorted array?
Just one, or?
What algorithm do we use? Log n, we use binary search. So to find the right place for it, we use binary search. And then to shift everything else back, what's the worst case runtime? O of n. So that ends up being O of n if we're using an array to do this. Now let's say we do it on the other side, removing something from the front. If we're using the end of the array, removing something from the front, or removing something from the end of the array, which happens to be the front of our line.
Right, that's O of n because you got to move everything forward.
Well, that's just O of 1 because we can keep track of where that end of the array is. But then we still end up with this O of n behavior for inserting someone because we do the log n search to find out where they go, and then we're going to have to shuffle everything down one way or another. What about for a linked list? Can you replicate this analysis for us?
A linked list, if you're just, removing the first item, wouldn't it just take one time because you just make the next one the new head?
And then insertion?
O of n, worst case, because you need to find the spot and then you just...
Yeah, so with a linked list, we don't even get the benefit of binary search because you can't jump halfway through the linked list and then split it into two and figure out which half to go to. Because all we know is the head, or if we're being extra fancy, then we know the tail, but we don't know where in the middle it is. So it's going to take us O of n, worst case, to figure out where to go in the linked list. And then we have an O of 1 insert once we've found the correct location, but it's too late. We've already done O of n work. So we do get this interesting kind of naive version number 2 based on our array implementation or based on our linked list implementation. But you had a kind of a fancier idea to begin with there, which kind of jumped the gun a little bit. So here is our 2 versions with insertion and deletion with the linked list. So you can look at these slides. But these aren't good, and Sam had some fancy ideas. He's like, this tree thing that we're doing, yeah, the way you were fixing that up looks like it wasn't taking so much work. So maybe we can use a similar idea, but with a slightly different rule to our binary search tree rule to get the properties we want, to make all the operations that we need to be more efficient. So there are always going to be some trade-offs with your data structures. The question is, given the set of operations that you need, can you come up with a data structure that makes the operations that you're going to do frequently the cheap ones? So here's another attempt. Let's try doing this with a binary search tree. This is just keeping the same property that we had before. And this is what we get. So insertion in the average case is going to take us log n. That's just the normal insertion in a binary search tree to find the right position. In the insertion in the worst case in a binary search tree should be, that's not correct there, that should be O of n. So to find any item in a binary search tree is also going to take us average case log n. Find any in the worst case is going to take us O of n in the case of a stick. Find maximum, now this is where things get interesting. Finding the maximum could take us O of log n, because you'd say, well, that you still have to follow all the paths. But if you know that find maximum is an operation that you're going to be doing frequently, what you can do is actually save the given maximum of the tree and then fix it up each time as you delete items. Let's say you remove an item from the binary search tree. If the item that you're removing is the maximum, then you need to find the next smallest item. However, in most cases, when you're removing an item, it's not going to be the maximum. And so when someone asks you for the maximum, you can just report back the one that you've saved, giving you O of 1 in most cases. Garv has a question. And then in the case of a binary search tree, we also have creation is going to take us n log n, because it takes log n for every item we want to insert, worst case, but then we're going to do that n times. So that's n items we've just inserted, and for each of those it's going to take us log n. Now, does anyone have any questions about that particular statement? If you're paying a lot of attention. And we will see a bit more of this in our analysis of our next data structure, which we call a heap. And we may or may not have time to go through everything we need to know about heaps. But heaps are similar to binary search trees in that they are binary trees, but they have a slightly different rule associated with them. So for the binary search tree, we had that the right subtree is larger than the parent, larger than or equal to the parent, and everything in the left subtree was smaller. So for our heap, we have a simpler rule actually, which is just that the parent is larger than all the descendants. So this means that none of its descendants, neither on the left nor on the right, can be larger. Everything must be smaller if you are the parent. So in our example, we have 100 at the top, and then everything under 100 is smaller. Let's pick a different subtree. Let's pick the subtree starting with 36 as the subtree root. Everything under 36 is smaller. And we can also put this in array, and just like we were talking about how we could either implement all our structures with arrays or with pointers, we can also do that with our heap. I'll get to you in a second, Tim. So in this case, we're just going to use a simple relationship between the position of parents and children in the array representation. So in this case, start with the root at position 0, and then its two children should be at 0 times 2 plus 1 and plus 2. So then let's do for 1's children is at 1 times 2, that's 2 plus 1 and plus 2. And let's do that for 2's children, 2 times 2 plus 1 and plus 2. And so we just have this relationship between each of the positions. So let's also look at 3. 3's children are not 3. The item in position 3. I should be much more careful about saying that. So the item in position 3, its children are located at 3 times 2 plus 1 and plus 2. So 100's children are at 0 times 2 plus 1 plus 2. 19's children are at 1 times 2 plus 1 and plus 2. And then you get the idea now. Now we'll go to Tim's question.
So the requirement here that the parent be larger than all the descendants doesn't make it obvious how you deal with duplicates. Because if you have, say, if I try to insert 100 into this heap, does it make an exception? Does it have like a requirement that, oh, if it's a duplicate, then it has to go left, or can it just be like, is it just that it's larger than or equal to?
Yeah, it should be larger than or equal to.
So you said that we can implement like a heap either through pointers or as an array, but isn't an array in of itself an abstract data type which is implemented through pointers? So then if you're implementing a heap through an array, can you implement abstract data types using other abstract data types?
So one thing you said was that aren't arrays themselves an abstract data type?
Yeah.
Arrays are probably not an abstract data type. They're just a data type, and the reason being that if you actually poke into what's happening inside the machine, the arrays actually represent contiguous chunks of memory. And it is possible to, like in Python, for example, that might not be the case.
Yeah.
But at least in C and for the purpose of algorithmic analysis, we're assuming that arrays underlying in the machine are just a single row of memory such that you can jump to any position. Okay. So the programming language is providing an abstraction in a sense, but the arrays themselves are actually like pretty concrete.
Okay.
Yeah.
Yeah, all right. I was just wondering, what's with the ordering for 19 and 36? It's there as 1 and 2 on the slide. I was just wondering, is it because it's in ascending order or is it just random?
It's just random. It's based on the order of insertion and deletion. You can end up with a lot of different configurations as long as this property holds. So there are some other ways of arranging these items, which means that we can't use our search algorithm like we used for our binary search tree, which imposes much stricter constraints such that you always know where to go to find a specific value. In this one, we don't have that property. So if I said, find me 19 starting at the root, well, say, find me 3 starting at the root, you don't know whether to go left or right because you know that 3 is less than 100, but you don't know if it's in the left subtree or the right subtree. Other questions before we move on? Okay, so we actually have 2 versions of this. We have the max heap and the min heap, and let's imagine they're a greater or equal to sign here. The max heap has the rule that the parent is larger than all the descendants, and the min heap has the opposite rule. The parent is smaller than all the descendants. Which of these you want to use is just going to depend on whether you are looking for the smallest item or the largest item repeatedly. So if we want to be if we want to have very, very easy access to the largest item, then we're going to want the root, which is the item that we're always keeping track of, to always be the largest, which means that it should be all the descendants that are small because we want the root to be the big thing, and then we can always get very quick access to the biggest thing. With the min heap, it's the other way around. If we always want to know where the smallest item is, well, that should be the root, and we need the smallest item to be at the top and all the descendants to be the larger ones. So for the time being, we are going to look at max heaps. This is just a choice so that we have to pick one of the 2, and we're going to pick based on our problem of giving tickets to people based on the highest grade, we'll pick a max heap. And so just compare this to binary search trees one more time so you don't get too confused. With our max heap, the parent is going to be larger than all descendants, and that's our one rule. Whereas with the binary search tree, we have this strict ordering such that the right child, not in the entire subtree, this is a rule that applies to parents and children, the right child is going to be bigger than or equal to the parent, which is going to be bigger than the left child. And so one way of thinking about it potentially is something like this. If you, in order of increasing strictness of the rule, you have a binary tree, which just says that you have this structure of every node having at most 2 children. Then you can have a heap, which has this general rule, which just says, well, all the descendants should be greater than or smaller. And then even a bit stricter than that is the binary search property that we have on our binary search tree. And that takes us to our algorithms for actually creating the heap. Now this is going to be, there are a number of different sub-algorithms that we're going to need in order to build our heap. The most important of these is the Sift-Down. Now the easiest way to start to understand this is we can start with an already constructed heap. I can show you the operations, and then from there we'll then go back and try and create our heap from scratch once we understand how Sift-Down works already. So I am now going to have to give me a minute, and I'm going to open up the iPad so we can actually do our... little sketch of this. Okay, so let's say we have this array. And using the rules that we discussed earlier, we can draw the picture of it. Again, when you're actually doing the operations, when we write it in code, we're going to use the indices of the array that correspond to these different elements, and we already talked a bit about how to calculate those. So the children, where you multiply the parent by 2 and +1 or +2, depending if you want the left child or the right child. But for now, we're just going to draw the pictorial representation that treats it like the family tree that we were doing before, just to make it a little easier to see our operations. So let's start off by drawing the tree that this array represents. So this is the following tree. So we have 4 with its 2 children, 8 and 7. And note that unlike our search tree, the only thing that we care about here is that, in this case, we're doing a min heap rather than a max heap, sorry. We're just caring about the fact that the children are larger than the parent. Next time I will make sure to keep us consistent with max heaps or min heaps. So we are going to start out with our root node, and we are going to do our Sift-Down operation. So we're going to start with this node and figure out how to get it to a place such that it is now in the correct place. And so what we're going to first do is let's start with our 4 over here and figure out a place to swap it to. If I'm doing a max heap means the parent should be larger than the children. Okay, let's swap it with the 8. So we have 4 and 8. Is 4 in the right place yet? Do we have a violation of our max heap property? Elizabeth says yes. Okay, Elizabeth, how do we fix this? Swap it with the 5. So out of its 2 children, the 5 is larger, which means that's a violation of our property. So we are going to swap the 4 with the 5. Okay, do we need to do any more swapping of the 4? Okay, so now we're fine with our 4. We'll see you all in a week's time, and then we will go back to finishing off heap sort. But we're out of time for today, so I will see you all in 1 week.